Okay, so today and tomorrow, the last two lectures, I'm going to switch to talking about compositional compiler verification. And in particular, how you're going to see how we use logical relations for compiler verification. I'm going to try to show you two styles of proof. But before I sort of jump into this, I've had several questions from people about, some of the other topics that I'm not talking about this year. So in particular, I asked you guys about mutable references, but I'm not going to be able to talk about that. So if you are interested, my OPLSS 12 lectures is probably around lecture 4. I did mutable references that year. If you want to see free theorems worked out or proofs of, showing two simple existential packages are equivalent, I did that last year. So last year's lectures, you can watch those. So gives me a chance to move on to new stuff this year. Okay? All right. And also there are lecture notes that one of the students last year took, which are now on the website, on the main website, not on Piazza. Okay. So compiler verification. So what do we want from compiler verification? So let's just start out with the most dead simple obvious statement of what compiler correctness should be. Okay, so basically what we're trying to show is that if you have a source program S and it compiles to a target program T, then S and T should somehow be equivalent. They should somehow have the same meaning. Now keep in mind, of course, that S and T are true programs in two different languages, right? So that's the part that's kind of tricky about this. What does it mean for two programs in two different languages to have the same meaning, right? So I mean, intuitively we say that they should have the same observable behavior when you run them. Seems fair, right? Okay, so that's kind of what we're after. And just to make it really clear, informally we all go around saying compiler correctness, okay? But there's a more formal thing that more formally speaking, the property that we're trying to prove is semantics preserving, that your compilation, okay? That the meaning of programs is being preserved, right? Semantics preserving compilation. All right. Okay, so how many people know about CompCert? All right, okay. So let me tell you about CompCert for those who don't. So compiler verification is a topic that's been worked on for more than 40 years now. Okay, it's not since 2006, as this slide says. On and off, there have been major projects that have tackled compiler verification, right? But in 2006, this CompCert paper came out, Xavier's paper at OPLSS, formal certification of a compiler backend, or programming a compiler with a proof assistant, okay? And this was the first one to sort of take a serious, compiler backend for C, for a realistic language and a realistic, compiler, not one that does, like super optimizing or anything, highly optimizing, but it, a legitimate serious compiler that had been mechanically verified using Coq, okay? So this was sort of a state change, I would say, in the research field. Suddenly people looked at this and said, wow, this is possible. Before that, it seemed utterly daunting to even try, okay? So there has been a lot of, this paper sort of led to a lot of work on compiler verification. Everyone, there are a lot of projects that started doing this. So let me just list a few. This list is by no means comprehensive, okay? There was a paper at OPL10 verifying a compiler for Java threads. I think it was OPL10, maybe it was ESOP10. Verified just-in-time compiler on x86. This is a sort of rather toyish just-in-time compiler, but still. There's this paper on CompCert TSO, which deals with relaxed memory concurrency. So it basically takes CompCert, but it's trying to tackle a back end where you have weak memory models. And then OPL14, there was this very nice paper on cake ML, a verified implementation of ML. So you'll notice that, we've gone from verified compilers for C to people tackling verified compilation of Java to people then tackling, verified compilation of ML. But today I want to tell you why we need to move beyond what's been happening in the following way. All of these papers on this slide do whole program compiler correctness. So the compiler correctness theorem that they prove says if you are compiling a whole program, in other words, a program that after compilation will not be linked with anything, then I guarantee that the meaning of your source program is preserved. Okay? All right. And basically, I'll get into the details in a second. So basically, all of these these pieces of work have kind of, they've experimented with different theorem provers. For instance, the CakeML work uses Hall, not Coq, and different strategies for making compiler verification easy. But all of these papers, at least, have all been about whole program compiler correctness. Okay? All right. So this is a problem, right? Well, this slide kind of says what I just said. All of those papers make this closed world assumption that you're not going to, that you're compiling a whole program, and they're only guaranteeing correct compilation of whole programs. But in reality, you almost never write a whole program, do you? Even when you think you're writing a whole program, you write the program. It's one of these components with something missing, the ES, okay? Think of ES. I'm using big P for whole program, and I'm using little e for some program expression or a component, okay? So little e's throughout today would think of it as a component, not a whole program, okay? So if you have a source component ES, and I claim that even if you think you're writing a whole program, after you compile it down, you at least link it with low-level libraries, right? The runtime library, things like that. There's just no way of avoiding that. So everything is linked. So we'd like to be able to guarantee correct compilation in those scenarios. And much more importantly, a vast majority of decent-sized software these days is built by writing components in different languages, right? So you write a different component, that red guy, in a different language, and you compile it down to the same target, and then you link these pieces together. So how do we guarantee compiler correctness in this world of, where you have to take linking into account, and you have to take multi-language software into account? That's kind of, I think, like the next thing. So the first slide said compositional compiler verification, right? Compositional here means correct compilation of components, okay? Not whole programs. In other words, you want to be able to compile a component, guarantee that it's correctly compiled, and sort of reason about what happens when you compose this component, link it with another component that might come from, that might actually be written in low-level assembly, like parts of schedulers are sometimes fine-tuned by hand, or it may be produced by a completely different compiler for a different language, okay? You want to be able to reason about this. All right, so why is it, now let's get to the crux of, why is it that all of these papers that I've mentioned make this whole program assumption, okay? So the whole question comes down to, let's dig down deeper into how this S is equivalent to T is expressed, okay? All right, how is it expressed? Well, in CompCert, for instance, and the other papers, essentially what you're proving is that relationship, you're proving a simulation. You're saying that if I run my source program PS, then that simulates the run by my target program PT, okay? So in particular, if we dive down a bit deeper, you're saying that at any point in the program, if I have PSI that's in a certain relationship with my PJT, all right, then if PS takes one step, then PT here might take one or more steps, and things are going to line up again. So it's all about showing the simulation argument that things line up. There's a little bit of flexibility in how things line up. You may let the target take more steps or the source take more steps, but you're trying to do this lining up thing with a simulation argument, okay? Now, notice how I said you run the source program PS and you run the target program PT, right? That brings me to the next question. How, if you're trying to guarantee correct compilation of components, how do you express this equivalence? And I'll start out with a naive statement. You can't run a component, right? You can run a whole program, but how do you run a component? A component is something that has a missing piece. You can't run it. You need to link it with something, only then can you run it, right? So just sort of intuitively speaking, that, trying to do this kind of simulation argument is a little, it needs to be somehow, strengthened. Okay, so how do we express that this source component ES is equivalent to this target component ET, all right? Okay, so let's think about how we want to use these compilers, right? So I want to compile a component, and then I want to link my compiled ET with some other ET prime, right? And I've already tried to motivate that this ET prime might come from anywhere, produced by a different compiler or whatever else. So however we define this equivalence between source and target, ideally, and this hasn't been done yet, okay? But this should be our goal, that this definition should permit linking with target code of arbitrary provenance. It comes from anywhere. And it should support verification of multi-pass compilers, because realistic compilers are always written in multiple passes. Okay? I know I haven't said anything about multi-pass yet, but I put this up here because doing both of these things at the same time is surprisingly hard. Okay? All right. And I said it hasn't been done yet. It has the beginnings of it. So we'll get to that by the end of tomorrow's lecture. All right. So correctly, now before I sort of dive into like what I want to talk about today. So today I want to do a case study. I want to take a particular compiler transformation, closure conversion, and show you how we can use a logical relation to prove that correct, all right? But let me just sort of say something about C compilers first, okay? So it's not that there are absolutely, by now in the literature over the last couple of years, there has been work on compositional compiler correctness, right? Correctly compiling components, but there's this work for C. So let's sort of look at the limitations. I want you to give you a sense of the landscape, right? The very cutting edge sense of this compositional compiler verification landscape. Okay, so there was this paper on CEP-COMSERT, okay? Separate, right? Separate modules being compiled and linked together. All right, so this paper on CEP-COMSERT, I have a very blocky figure up there, but let me tell you what it says. Its compiler correctness theorem says the following. It says that if you have two separate blue components and you compile them using the exact same CEP-COMSERT compiler, okay? So you're compiling them from the same source language using the exact same CEP-COMSERT compiler. If you do that, then you can link them together over here. So the compiler correctness theorem, the way that they state it, allows you to accommodate that form of linking. So I would call this separate compilation. Same source language, right? You're not linking with anything that comes from a different source language. And you can't link with anything that comes from a different C compiler even. Okay? So let's call this separate compilation. And let's make a distinction between separate compilation and, let's say, more compositional compilation where you can link with things that come from different languages and different compilers. Okay, so that's what CEP-COMSERT does. And if you look at the paper, they make a very big deal about like, what? Oh, there's a question, yes.
Static linking or dynamic?
Static linking, yeah. Mm-hmm. Yes.
So how does this interact with runtime systems? Currently, all our examples talk about C, which does not have a runtime system.
But you want to link with low-level C libraries.
Yes, we want to link C, that's
Mm-hmm.
good.
Yeah.
And we can link C.
Yeah.
But even not worrying about verification for a moment, linking languages with expressive runtimes is a very complicated task if you don't write that.
I completely agree, yes. And we'll come back to this.
Is this a requirement? Is this subsumed by one of the existing requirements?
Existing requirements of what? Of this particular one?
Well, there were previous slides, there were requirements.
Oh, I see. These two requirements, well, multipass is not what you're talking about. You're talking about linking with arbitrary other code. It's a difficult question to answer exactly at this point. Okay, but let's come back to that. All right? You can set yourself an ideal goal of wanting to link with absolutely everything, but in reality, the research is going to take steps a little bit at a time, and slowly we're going to try to get there.
You also had ML on the previous slide, right?
I had ML on the previous slide, but CakeML does not allow you to link with other code. Yeah. Okay. All right, so let's get past CEP-COMSERT. CEP-COMSERT only allows you to link with C code that's compiled by the same CEP-COMSERT compiler. Then, a year before that, there was compositional COMSERT, okay, out of Princeton. So this is actually far more liberal. Again, it's a C compiler, it's COMSERT, right? It's an extension of the original COMSERT compiler. But what this allows is, it says you can compile C components down to these ETs and then link with other ET primes with other low-level libraries, okay? And this is actually very nice work. It lets you link with any other low-level code, okay? But it's not time to go home yet. We're not done. And let me explain why. This is a C compiler. And the way that compositional COMSERT works is it relies on a very beautiful property that the COMSERT compiler has had since its inception, which is that all of the languages of the COMSERT compiler, all of the IRs from source to target, they all have the exact same memory model. Okay? And you can do this because C is a rather low-level language. You can have the same memory model as your assembly will have. Okay? And this has actually made the task of doing this mechanized verification for CompCert surprisingly, I won't say easy, it's not easy, but doable. So this work relies on that same memory model thing. And we don't have any idea how to scale the ideas used in this work to move to languages which might have a different memory model. Now, why am I bringing this up? Because I'd like to be able to compile ML in a compositional way. What you just said, right? Like, we'd like to be able to compile ML down. We'd like to be able to link with the runtime. We'd like to be able to link with other code. Not just ML, typed languages. And higher level typed functional languages, right? We're talking about a different memory model. These are not C. So, as proud as we are of the work on CompCert, one could say that, C is a rather low-level language. Like, you're already starting at a rather low point in your language, in your compiler pipeline. If you think about how do you get yourself from ML, correct compilation, all the way down to assembly. There, things are harder because the languages are so different, right? Your ML memory model, your assembly memory model, there's a serious gap there. Okay, so just to give you a sense of that. Okay, so there's still work to be done. Typed high-level functional languages, let's say. All right, that's kind of the thing that I've been looking at recently. So let's talk about this. How would we now express this sort of property, right? Our compiler correctness theorem, again, says ES compiles to ET. How do we express that equivalence? So again, back to what we want out of this theorem is that we want to be able to link with this arbitrary ET prime, all right? So now I'm going to transition off into one approach to solving this problem, okay? And tomorrow I'll talk about a different approach. So one approach to solving this problem is you set up this equivalence as a cross-language relation. And I already hinted at this in my first lecture, right? So you're going to set up a logical relation between between source components. You don't have to do whole programs with logical relations, right? We've been seeing that. And this is an approach. So again, this approach, the fact that you can use a cross-language logical relation to talk about the correctness of translations, this is something that has been around for decades as well. But for decades, people did this only for very idealized toy kind of languages, okay? Terminating languages. I think if you go back to like the late 90s, there's a published proof of, for like type closure conversion is correct using a logical relation, but the languages are terminating. And there's a lot more in the literature, but always for small toyish languages, okay? Or not for realistic compilers or anything. So the reason I have these three papers up is because Benton and her ICFP09 were the first to make this a bit more realistic. I mean, even they have their target is an SECD. They go from a functional language to an SECD machine. Even that is not utterly realistic, but it's sort of touted as the first somewhat realistic compiler.
SECD machine?
Oh, help me out here. Stack, expression, I never remember the acronym. Control dump? Is E for expression? No, I'm looking at you. No one remembers. We get so used to saying SECD machine. It's an abstract machine, and it has 4 different pieces. It's meant to simulate computation. There's a control stack and so on. I can tell you afterwards. Does it have a memory? Yeah. Sort of. It has a list in which you look up things. Yeah. And by the way, this paper was not about compiling a language with memory. The source language was functional. It was simply type lambda calculus or something, but with non-termination. Okay, so yeah, so there are these other papers. And by the way, this last paper at ICFP 15 last year is not a logical relation per se. It is an interlanguage simulation. It does not use but interlanguage means cross-language, and simulation means not quite logical relation, but a different sort of simulation. I'll come back to this by tomorrow. Okay, let's think about why we want to use a logical relation to do this. So I want you to think of the compiler. So what's happening on this side is I have a component ES of type tau. It type checks in an environment in which I have put just one free variable, okay, x. That x colon tau prime is like it's a stand-in for an input that your component ES is waiting for. That's the sense in which my ES is a component, not a whole program. If my environment there was closed, there was no x in the environment, then I'd have a closed program, right? Okay, so start with that principle. Open programs are programs that have free variables in them. Okay? And now we want to express compiler correctness for these open programs. Because open programs correspond to components, right? They haven't been fully plugged in with all the other things that they're going to be linked with yet. So when you think about linking, I want you to think about it as, okay, I'm taking ES, which has a hole in it marked by X. I'm compiling it to ET, and somewhere inside ET there will be a hole in it marked by maybe not a variable X, maybe it'll be a register if you're in assembly, right? But there will be a particular point where you will plug in a separate, a different component that comes from somewhere else. Okay? All right. So linking kind of becomes substitution, right? Okay, for your free variables. All right. So if this open component ES compiles to ET, then we want to show that ES is logically related to ET. My funny symbol there is a logical relation. All right. It's a cross-language logical relation. That's why I'm not using a double squiggle. I was trying to sort of distinguish this. Okay. Let's switch to the board now. Okay. We'll do type closure conversion using a cross-language logical relation on the board for the rest of the lecture. All right. Okay. So, how many of you know what closure conversion is? How many of you know what closure conversion is? Okay, I will explain it. All right. Okay, so let's start with this imaginary scenario. Suppose that we have a source language. Let's make our source language. I'm going to try to keep things simple so that I can get the main ideas across of using cross-language logical relations, all right? So let's make our source language just be the simply typed lambda calculus. I can add recursive types to that. I'm going to use sigma for types today. Maybe I shouldn't. Maybe I should just use tau. I'll use tau. Okay, so I'm going to use black tau for source types, and later I'll use red tau for target types. Okay? You're going to want to see that these things are different. Okay, so my source language, let's say we have integers in it, and we have function types tau arrow, tau 1 arrow, tau 2. Okay? And if you want, I can totally throw in recursive types as well. We can do that at the end of the lecture if we still have time. All right? Okay, let's just start. We'll make this a call by value simply type lambda calculus like we've been doing the last couple of days. The values in this language, value forms, okay, variables, numbers, n, lambdas, x colon tau dot e. Expressions are all the values that I've written on the line above, plus I'll give you an if zero instruction. So if zero, because I didn't put booleans in today, I have integers. So let's do an if zero instruction. So if e is equal to 0, we are going to jump to e1, else we are going to jump to e2. Okay, that's the semantics. I'm not going to write the then and else. Save time. Okay, and then of course we have application. E1 applies to E2. Okay, that's our source language. Now, what is closure conversion? Okay, so the idea of closure conversion is that in your source language, when you start to compile your source language, you have to take arbitrary expressions and start translating them to target expressions, right? And this proceeds in a sort of structurally, by structural induction on those things. Like if you were trying to compile an if expression, you would go translate the E, you would go translate the E1, and you would go translate the E2, and then you would put them together in the right way to produce the compiled code, okay? Now, as you're doing this, you may run into some E that you have to translate that inside it contains a function, okay? And that function may have free variables, right? Because you could easily have code like, okay, I'm in some outer function scope, and then somewhere deep down in the body of this function, I have another function where, you know, I'm doing something like not z plus, maybe make this an int, z plus x plus 1 or something, right? But notice that this lambda itself, this function itself, is not a closed function. It has a free variable in it. This guy is bound all the way out here. So when we get to this point in the program and we start translating, we are going to run into functions with free variables. Now this is a problem. And the reason that it's a problem is because of what's going to happen much later in the compiler. You are going to take functions that you start off with functions in your high-level language. You're going to translate down, and at some point you're going to have to take those functions and plop them down in the heap, because a function cannot be stored in a register in assembly language. Right? Good? Okay, they're too big. Same thing happens with tuples. If you have tuples or pairs in your source language, a pair or a tuple cannot live inside a register by the time you get down to assembly, and therefore you have to take these things and put them on the heap. Okay? Now, in order to put these compiled functions on the heap, you can't put open functions in memory. Where are the free variables bound? You see what I'm saying? That's why you have to do closure conversion. Okay? So, yes? As in you closure convert, you turn them into closures, and then you hoist them up to top level. Yeah, precisely. Okay. All right. So let's look at one concrete example before I dive in and show you a translation. In fact, I'll show you two examples. So suppose that we have a function like this. Lambda x int x plus y plus, I don't know, w. All right? Here's a function. Clearly it has two free variables, right? X is bound here, but y and w are free in this function. And we need to closure convert this function. So I want to show you like what the basic idea is before we dive into the translation. So what is the basic idea? The basic idea is you take this function and you transform it into a closure. What is a closure? A closure is a pair of two things. Okay? You have a function that now takes not just its original argument. Okay, so you have a function which is closed code, and you pair it up with its environment, which contains all of the values for the free variables. Okay? So two pieces. That's what a closure is. So what you want to do is you want to transform this into something that takes a z. This corresponds to some sort of like whatever your environment is, in the sense that here y and w are free. So we need to somehow put them into, keep track of them in an environment. So I'm going to turn the code into something that takes an environment and takes the original argument. Okay? And then I'm going to, let's come back to the body of this in a second. I'm going to pair that up with the actual environment y and w, so to speak. Okay? All right. So that's what a closure is. It's a pair of a closed code, closed function, paired with the environment that the function needs in order to run. All right? Okay, so now what exactly do we need to do to the body of this code in order for things to work right? So now this code cannot refer to y and w. That was the whole point. Instead, it's going to refer only to its environment z, which is passed to it as an input. So the idea is that at some point in the program, when you are about to apply this function, you're not only going to give the function its input, you're also going to pass in, you're going to take this piece out of the closure and pass it to the function. That's the sense in which the function is closed. It takes all of its originally free variables as inputs, as an environment input. Okay? And so now what happens is that, well, we'll have to transform the body. We still have x, but we can't refer to y. But where is y? Y lives in z, right? It's the first component of that environment tuple. So we're going to do project the first component from the variable z. Okay? This is a stand-in for our original y, right? And then we are going to do project the second component from, again, our environment z, and that essentially is a stand-in, for our original w. Everything good so far? Okay. All right. So that's the basic idea of closure conversion. Turn functions into pairs of functions in their environment and transform the function so it actually takes the environment as an input. Now it's closed code, and you can go put it anywhere when you eventually get to allocating functions on the heap. Okay, let me give you one other example. Let's do something. How do we closure convert that piece of code? Someone want to state something obvious about that piece of code? It's already closed, right? Okay, now, it's already closed. But if you're writing a compiler, you have to be uniform with respect to how you transform every single function. So if you are saying that now now your protocol for how you call a function is changing in your target language, right? You're saying that I'm going to take functions and I'm going to turn them into these pairs of function and its environment. You've changed the calling convention for functions in your target language, right? You're sort of saying that the norm, the established protocol for calling a function in the target language is to take one of these pairs, take it apart, take the second component of the pair, pass it to this guy, pass it to the argument, etc., then run. So if you transform that closed code and leave it unchanged, you're going to be in trouble. So you can't do that. So you have to actually closure convert it, even though its environment tuple is going to be empty, right? So you're simply going to turn it into a closure which has, again, just lambda z tau n x colon int and x plus 4. We don't need to use z, right? And we're going to pair this lambda with what environment? Empty tuple. There we go. Okay? So that's our closure. Yes?
Is the target calling convention important here, or could we have standardized it either way?
You can't standardize it either way because the whole point of this pass is to do closure conversion. So you have to produce closures because you have to accommodate the scenario where functions might have free variables.
You could also encode a closure with a function with a new body, as a function with a new body.
What does that mean, though?
You write the code that has the variables x and y inside the new function. It doesn't not explicitly a tuple implementation, so the caller can call it as.
No, you can't do that because I gave you an example of that earlier, right? Like this function has somewhere very far outside a lambda y and a lambda w. And I need to turn this function into something. I can't pull those y and w and put them in. I just can't do that. We can go through details afterwards if you like. Right? I don't know. Do other people have the exact same question? If you do, then yes.
I think what he's saying is like just add two arguments to that thing and have its caller pass it w.
Oh, so instead of z, you want a no?
Yeah.
No, that's not what he's saying.
Yeah, that's also a reasonable thing to ask.
Okay, let's answer that one. Maybe I haven't understood your question properly. I'm going to try to answer that one. So you're saying why not make this a lambda y, lambda w, lambda x, etc., and leave this as a lambda x, whatever, right?
Yeah.
Okay. Excellent setup for my next point. What is the type of this function? Really already? That's good. What is the type of the function? What is the type of this function? Okay, now regardless of whether you take my proposal or his proposal, we're going to get stuck. My proposal is not done yet because it was just halfway attempt. Okay, let's look at what is the type of this closure. It's a pair, right? So it's a product of two things. It is a function that takes a tau n. Let me start writing functions that take multiple arguments. Okay, so I'll write it a function that takes a tau n and takes an int and produces an int, and we are pairing that function with an environment that is an int paired with an int. Good? I should probably not write x, times here. I should just make it a comma if I'm using tuples, but never mind. You get the idea, right? Okay. How about this guy? What's the type of this function? It takes a tau n, right? And an int. Gives us an int. And then it's paired with, sorry? Empty tuple. Okay. And what is tau n in this world? Here tau env is actually just a stand-in for an empty tuple type. So let me do that. And here tau env is a stand-in for int, comma, int. So, and this is exactly what would have happened with your proposal, right? We would have been taking an x and a y here. Maybe we would still need that. X and y here, and here we would be taking nothing, but then you just have int arrow int function, right? What am I pointing out, or what am I trying to point out? You have taken two int arrow int functions and turned them into two functions with completely different types. How does this make sense? Right? How? Yeah.
And the low-level representation doesn't need to be typed in there.
Yes. Okay. So I want to do typed closure conversion today. Okay? So I want my low-level representation to be typed. So partly this is a tutorial on a paper that happened back in 97 or 98, which is called Typed Closure Conversion by Minamide, Harper, and Morissette. Bob was one of them. So this is, I'm sort of trying to explain the basic idea of that typed closure conversion. How many of you have ever seen is there a question there? Yeah. Yeah. Yeah.
So if we were to take a code for these free variables, abstract it not in the lambda, and then apply that resulting lambda to variables outside, then I kind of don't see where the problem is, because you're transforming your simply type lambda expression into another one that has no free variables inside lambda, and the entire expression, because you applied it to those variables in the end.
Yes. Yes. And in some sense, this is analogous.
Yeah.
Right? Yes. Yes. Exactly. Sorry, I was about to mention this paper called System F to Typed Assembly Language. All right. If you haven't read it, you really ought to read it. It is a seminal paper that you guys should not be getting PhDs without reading. Okay. What that paper does is basically it shows the idea of a type-preserving compiler, that you can take a typed language and preserve types at every single level of your compiler all the way down to the assembly language. From System F to Typed Assembly Language. Read the journal version of that paper, not the conference version. Okay. It was in TOPLS, I think. Okay, so the idea of typed closure conversion is that, well, if you're producing typed code after your closure conversion pass, then you need to be able to have the same type for both of these functions, right? The fact that one has more free variables than the other should not matter, because, that's going to be a problem. So the way that that's achieved is by using existential types to hide the type of the environment, okay? So what we're going to do is we're not going to just produce this pair. We're going to take this pair and we're going to wrap it up into an existential package, okay? And the basic idea is that this int arrow int function, instead of having that there, we're going to have an abstract type environment in its that it takes as an input, and we're going to put the type alpha represents the type of the type environment, and we're going to put an existential out here. Okay? So what are we doing with the existential types? We are saying that an int arrow int function turns into a closure, and a closure has an existential type that hides the type of the type environment inside the package, because it's local to it. No one should care what it is, right? This type now allows you to accommodate both, zero length environments as well as, longer environments, bigger environments, right? So this would again turn into the same exact thing. And now you have a uniform, from a type perspective, a uniform representation of closures, and inside the closure, inside the existential package, you're hiding however many free variables you have, okay? So this is the essence of type closure conversion that you get from that paper. Okay, so basically, let's get back to our source language and start to see how we would uniformly define a translation that accomplishes this, right? And again, we're doing typed closure conversion, so we're going to have to take types in the source language and translate them to types in the target language, right? And then we're going to take our source program, E, and turn it into a target program, let's call it ET, that such that if the source program has type tau, then the target program has type translation of tau. Okay? All right. By the way, so you noticed that in my target language, I'm going to need to have existential types, right, to represent the closures. My source doesn't have them. But this is again in line with sort of using richer target level type features to type check low level code. Often those richer type features are convenient for laying out various protocols and things about low level code. And that sort of starts to show up. what does pack do? Pack creates a pair of a witness type. Pack creates a pair of a witness type and an expression. Maybe I should write that. Pack. Let's do the pack. So. Okay. Okay, someone want to tell me how you do the pack typing rule? What type should E have? Yeah. Yeah, so E has to have this type tau, but this type tau can have alpha free in it, so you need to plug in the tau prime for that alpha.
Sorry, that's like
This one is the normal tau, yeah. That's this one, sorry. Okay, and what does unpack do? Oh, and by the way, here I'm assuming that that tau prime that we're plugging in is well formed in this environment. So pack is basically taking a witness type. It's like creating a package. It's saying, I have an expression. I know that its type is this much more detailed, specific type. Tau prime might be in it. I'm going to hide that in from you and just call it out. I'm going to give you a package that hides that type. And you get to go play with that, but you can never actually know what the witness type is that's hidden inside the package. That's why I always think the type is a pair of a witness type and the actual thing that you're putting inside. Okay. Here are this and code. You know much more about the code really, but you're trying to hide it using this extension. Oh. Okay, how about an unpack? Okay, we unpack a package, right? So in this position, E1, I expect E1 to be evaluated down eventually to some sort of package. And then what the unpack does is it takes those two pieces of the package out. It takes the type out and calls it alpha. It takes the value part out and calls it x. And then this alpha and x can be free in the body of the unpack, but you have to refer to them as alpha and x. You can't really know it. Okay? All right. So let's write down first. We want our E1 to be a package, which means it has to have an extension. Okay? What about E2? Now, I already said E2 can have alpha and x free in it. So we're going to have to add them to the type environment because we're going to right? So take delta, add alpha to it. Take gamma, add x colon what? Remember this thing is an exist alpha tau, so x has to have type. No, we're not trying to, we want you to use the package without knowing what the tau prime is. You're never allowed to know, you being the client. And I want you to think of E2 as some client who's trying to use a package. Let's take an example, an abstract data type, like stacks, okay? We write interfaces for stacks all the time, right? A stack interface can have a push, pop, push method, pop method, right? And some sort of internal representation of stack. So you write a stack interface. Then you can go and write two separate stack implementations. One of them might use an array on the inside to represent the stack. The other one might use a linked list on the inside to represent the stack. In instance, those interfaces are existential types. The interface is hiding the concrete representation of the stack, in this case by calling it alpha, right? So one stack is using an array to represent the stack, in which case tau prime would be that array type. The other stack is using internally a linked list to represent the type, in which case tau prime would be that linked list. Now when you go and use a stack, you're not allowed to know which representation is on the inside. You have to write code to the interface, right? This is the essence of modular programming. This is how we build big software systems. And this concept exists in all of these languages, like Java has interfaces. So existential types are what we call abstract data types, are the same thing as interfaces, right? It's about hiding something internally, hiding the representation from all clients, and then forcing those clients their code won't type check if they're trying to take the stack representation and sort of go and do an array reference somewhere inside. See what I mean? Now, coming back to their code, this is your client, okay? This is some client that's, let's say, trying to use a stack implementation. That client has to type check under the assumption that X has some type tau. Tau has stack representation is still called alpha. So when I type check E2, E2 does not know anything about the concrete representation of my stack. It does not know what that tau prime is. It does not know. It only knows it as an alpha. So it can call the push method and the pop method. Just pass around alphas, right? But it has to treat this stack as an abstract state log that kind of passing around. And the only code that actually deals with the internal representation is the code that you wrote for the stack itself. Okay, this turned into a really big digression on existential types. But if you hadn't had it before, I hope that was helpful. Yes?
The bottom line there, that should be unpack tau x, right?
No, alpha x. So in other words, if this guy was a pack tau prime e, right? You want to call, let's write down the operator sentence too then. You want to refer to the tau prime as an alpha. You want to refer to that thing as an x. Okay, let me show you.
Where did the tau on the line go?
All right, hold on. Where did what go? This tau is coming from this existential, and notice that this tau can have alpha 3 in it, but you put alpha in the environment, so this tau is allowed to have alpha. And there's more. This thing needs to have type tau2, but a really important rule for unpack is that this tau2 cannot leak out of this alpha. So tau2 has to be good under delta. Notice that our original delta does not have alpha. It's like this. That is not what is in the original delta. Okay? And this is really important. You can't, because otherwise you'd be leaking out this representation tool. And there's a ton of work on how, these really are interfaces. How would you take Java interfaces and like compile them down or something like that? That kind of ties all of those ends together if you're interested in that. Okay, so how does unpack work? Why is this an alpha? Because the actual primitive reduction rule that happens, remember I said this E1 will eventually evaluate to a path? So I'm just going to put a path right here. If I'm trying to unpack a path, which is a tau prime to a b, as is the tau prime, and then use it in the body here. So imagine E2 is my client. What will happen? Well, we will start running E2, but we'll start running it with tau prime for alpha and b for x. So now we're telling E2 what it is, right? At runtime, E2 knows what that internal thing is, and E2 knows what the value that's sitting inside the package is. But, okay, so what? At type checking time, E2 type check, promising to treat that tau prime in an abstract manner. This code won't type check if it performs any kind of operation on this value. Like if this was actually an alpha, this code can't do it. So that's the whole speed there, parametricity, all that stuff that okay. That was a very big digression. Let's see. Back to the closure rule. So what I want to enforce is when I type check my lambdas, the body of the lambda has to be closed, which means that when I type check this body, I can't take any of the free variables. I have to type check it only under, I can add all the actual inputs to the function. Here it doesn't have any type variable inputs, so I'm going to put a dot in that environment. It can type check under all the inputs to the function, but nothing else. Otherwise, it has to be. Okay? now the type system and target language is enforcing what we want, really. And this is a good thing because, as you implement your compiler, if you design these, okay, back then, in around the end of the 90s, type preserving compilation was happening, and like systematic type assembly languages. One of the things that compiler writers were most excited about is that if I design type-intermediate languages for my compiler, then, and those typing rules are enforcing certain checks, like making sure that my code that I produce is actually closed, then I can just use type checking after I write my compiler to find bugs in my compiler. And we've come a long way. But this was like a super, thing that people were excited about. Okay, now, that's our target language. Let's talk about the type translation. So we want to take source types and translate them, and I'll write it like that with a plus. So tau is the source type, tau plus is the translation of that, and it will produce a red type. Okay? So if I have integers or closure conversion, I will want to produce an integer. Integers don't change. Right? The whole point of this compiler pass is to take lambdas and close them. So it's just remain int. If I have a tau1 arrow tau2, how do I translate that? Well, what do you think?
There exists
an alpha. Now we want a pair of two things, the code that also has to take the environment and the environment itself, right? So we want, it takes the environment, and then it takes the translation of tau1. What does it produce? The result type. Tau2 plus. Right? Okay, so now this part is my function type, and I'm going to pair it with the environment, which is the alpha. Okay? Since we really only have these two types in source, we're done. I mean, if you throw in more, they would all proceed by subtraction reduction. If you had tau1 plus tau2, you would get tau1 plus tau1 tau2 plus, right? And the rest all. Okay, so now we want to write our compiler. And since this is a type preserving compiler, I basically want to do this one. I want to say that if you have an equal tau, the type transcending gamma, in the source, okay, a typed term, I'm only translating these both type terms, I'm going to compile it to some target thing, red E. I want to give you the shape of my translation judgment first. Okay? I'm going to produce this code such that if I took the environment and translated all the types in it, then this translated code would have translation type tau plus. Oh, and I also need to put a dot here because the judgment for my target language says that I need to have a delta, right? Everyone with me? Okay. So this is type preserving compilation. You're trying to make sure that when you produce code, this property always holds. Okay? That the code that you produce is well typed, it is a translation type if you translate all the types in your environment. So let's translate all the types in our environment before we go any further. So how do we define gamma plus? Well, when you translate a dot, you get a dot. When you translate gamma with x equal to tau, what do you think you get? You get a red x. Tau plus. Okay. All right. Now let's do our term translation. Okay. So let's just if you have a black variable of that type, gamma, then it translates to a red X. And notice, here I'm just going to write red X, but you have to keep checking all along the way that if will that thing type check under my translated environment? And you can see that it should, right? But I'm doing something. I'm changing the type of my variables. I'm not just changing black X's into red X's. I'm changing those red X's to have translation type. They don't have type tau, type tau plus. Right? So basically what's happening, remember I said these variables are little placeholders where you're going to put in the code that you end with? So as you compile down, you're turning your placeholders into the right translation. And that's kind of key, because you have to uniformly change representation. Okay, how about another simple case? N of type int, compile to red N. If 0, E1, E2. That's how. Let me compile that.
Zero, ready, ready one.
And where do I get those red E's from?
Gamma is
I need to compile it, right? So I need to take E, it is of type int, and I need to compile it to get my red E. And then I need to do the same thing for E1, which is of some type tau, and I need to compile it to get my red E1. And same thing for E2, right? I won't write it. Whatever, same thing. You also have to translate to E2, and then you take all of those three pieces and you put them together. So it's completely complete. Right? So far, everything is good. We're just sort of proceeding by process. Okay. Now let's do the two hard cases. So what do we have left? Where's our language? We know how to translate variables and numbers. We haven't done lambdas yet. We've done it. Now, so lambda and application, those are the two hard cases because this is closure conversion is a task that operates really, that transforms functions. So let's do that. I'm going to erase these cases. Okay, so one translated lambda x colon tau dot in, which has type tau arrow tau prime, which has type tau arrow tau prime. Okay, you want to translate that into some sort of red. What kind of code do you want to produce now? What type will the code have that I want to produce? That is the standard. So we'll have to produce a path. So we know that we'll have to produce some sort of a path. Okay? In the path, we'll have to path the environment, type for the environment. Right? That will be our first piece. We don't know what this is yet. I'm just going to put in a placeholder. We'll calculate it in a second. Right? But it will have to have some sort of type of the environment. So let's kind of go above the line for this page and start figuring it out. Well, since closure conversion, the first thing we have to do is we have to go look at this function and figure out what all the three variables are in that function. Right? Okay, so I'm going to say, let's assume that y1 through yn are the free variables, free-term variables, of our lambda x colon tau dot. Okay, the y's are the free things. All right. Now we need to know what the types of those y's are so that we can figure out the type of our environment. So that's the goal, right? Okay, so what we want then is, we want to do something like, well, all of these yi's, I'll just write I, 1 through m. Suppose that they have type tau I. Okay? For I, 1 through m. Okay, so now we have we know the types of the free variables in the source code. So now we can actually calculate what tau n is. What is it? What should it be?
Tau 1 plus
Yeah?
tau 1 plus tau 2 plus tau n.
Plus. Yes, they need to be translated, right? Because we're going to keep those black y's, and in the code we produce them and turn into red y's. Okay? Okay, so that's the type of my environment. If I want to be really, really super good with my colors, really I should be writing that. Okay? And it helps to see that. It really does. Okay. Now, so we know what tau n is, but now we have to figure out the pair of the function and the environment that we're going to put over there, right? We know what the environment is going to be. It's going to be a bunch of red variables. But we have to figure out what the function is. So at some point we're going to have to go translate this guy, right? The body of the function. So let's do that. Body of the function. Type checks under gamma x colon tau. And we know that it has result as tau prime. This is the thing we're going to translate. We're going to translate it into some red E. Now, quickly remind us, this red E needs to type check under these assumptions. That means, first we know that this E has a whole bunch of black Y's in it, right? So that means the red E will have a whole bunch of red Y's in it. Correct? Okay, good. What else? We know that this will also have a red X in it, because again, that's in the environment. Okay? So it's got to type check under all of those things under the translation. The red term. Okay, so let's try to figure out, here I'm just going to write, we have to pair this with some V, which is going to be the function we want. I'll write VF if you like, function part. And we're going to pair that with red I's. Right? That's basically what we want to use. So let's figure out what this VF is. What is our lambda? Well, it has to be a red lambda. Has to take the environment as an input. Right? If you look at the translation type, has to take the environment as an input. So it's going to be equal to tau n. Right? Because tau n is the witness type. Then it has to take the original variable s translated as an input. And then what? Now we have to transform the body of the code too, right? How do we transform the body of the code? Basically, this guy is referring to a whole bunch of black Y's. This guy needs to refer to those as red Y's, but we can't do that, right? We can't let this talk about the red Y's. We have to replace those red Y's with projections, the appropriate projections from the environment.
Substitute yi, or substitute projection
Projection
I,
I.
z for all yi's.
Okay. That's a carried straw for type closure conversion. Right? But it's systematic. The types guide you. They tell you exactly where to go. Once you have something on the type translation, yes.
Where did the red y come from?
Where did the red bar come from? So it happened by magic in this translation. So I said, sure. Basically the whole translation is defined. Under the base case, we turn black X's into red X's. So when we translate this code, this code right here, in this environment, we know that there are these guys, y1 to ym, are sitting right here in this gamma. So that means that when you start translating this code, at some point you're going to hit those black gammas, and you're going to turn them into red gammas. And so the code that you get out needs to type check under that translated environment. So basically, I'm relying on the fact that I know that this red E last thing, which is application. Okay, you just did lambda, just did application. Application is a little easier than the lambda, so okay. If I have an E1 applied to E2, they have type tau, under the assumption that E1, I want to translate this nicely, under the assumption that E1 has type, let's call it tau 2 tau. I'm going to translate this something. And E2 has type tau 2. I'm also going to translate this something. Right. So this should be somewhat complicated, right? You have two pieces. Go translate E1 into a red E1. Go translate E2 into a red E2. Notice that this is going to have type tau 2 plus. This is going to have type translation of this function type. Tau 2 to tau plus, which means that the type of this is an existential. Let me write it down. The type of this is exists alpha, and then a function that takes in alpha and tau 2 plus, and returns a tau plus, right? And then that is paired with an alpha. Okay? All right. So we have to somehow operate with this guy, and we have to do an application. We have to take the function that's stored inside this package and apply it to its environment, which is also stored inside the package, and to this argument, to the translation of E2. Right? So let's unpack. I'll call it P for pair, because we know that what's inside is a pair, right? A pair of a function and the environment. So we're going to unpack the E1, right? And then, in the body of this unpack, we're going to say, take the first piece of this pair out. I want a P. That's it. Right? Now, that function wants two inputs. First, it wants the environment. How do I get the environment? By 2 of P. Right? And then the second thing it wants is the actual argument, which is the translation of E2. This guy. And that whole thing should have type. Should have type x. Check it. Okay. All right. How much longer do you guys want to wait for lunch? Let's see. When did we start? We started at maybe about 8 minutes or something to 11. Should I go for another 10? Yeah? Okay, so we've written our right, our translation of type coded word. Now we want to prove it correct. Right? Okay. What we're going to do is set up a logical relation between source terms and target terms. Okay? But just like this entire translation is, you can see it's completely directed. This translation is so driven by types of the source type. Right? It doesn't matter that the target has extra things. Basically, what we're interested in specifying is for everything that, at the source side, for every source term with a source type, we want to relate it to target terms of a translation type. Those target terms of translation type might have lots of things inside them, like they might be using these universal types inside, or funny other uses of existential packages inside. But we don't care about that. We just care that when you type check them, they have translation. Okay? So what we're going to be doing is setting up a logical relation, and I'll start with the value relation. Okay? What we want now is something of this form. We are driven by source types. So the value relation is going to be indexed by types from the source side, not the target side. Right? And we are going to basically want to define this as sets of when is a source value related to a target vector. Okay? Let's start putting S and T here, would that be better or you? Yeah? Red, black, fine, okay, all right. Okay. So I'm going to set this up so that whenever we put a black value and a red value inside these relations, this guy is going to be closed, and it has to have this type tau, as you'd expect, to be of type tau. And the red V needs to be also closed. Now, delta environment closed, gas environment closed. And V needs to have type, what do you think? Translation of type, right? Not just any arbitrary red type, that's not allowed. Particular red type, which is the translation of this one. So we're setting up a relationship between things of type tau and things of type tau plus. Okay? And then we can have, I'll just put this invariant at the very, very top, and I won't repeat the typing requirements and all of the other relations that I read. Okay? So let's start. What value do I put in this relation? The integer. And when should they be related? When should they be equivalent? Have the same meaning? When they're exactly the same range. So if it's a black flag and a red flag, right? So I'm writing this. Okay. All right. So what values do we want here? What are the source values of type tau in our attention? What are the target values? What is the shape of the target values of type translation of tau in our attention? Packs, right? Packages, the value from the pack. Okay. And we want values in here, right? We said we want values. So it has to be a pack tau E, not a pack tau E. Pack tau E is an expression, it's not a value. Right? We're building the value relation right now. So it has to be some kind of a pack. You know, with the right translation. It has to have this type. So this becomes the tolerance of expression. Right? So what's the witness type? A witness, right? Type witness, sort of tau n thing. We're going to have two things after that. We're going to have the function, and it's going to be paired with actual environment. What are all these pieces of? What can we tell about them based on? What is the most that we can tell about the shape that they will have, based on the fact that we know that whatever we're trying to produce, let me change this, is actually a tau 1 arrow tau 2. We're trying to produce something of this type right there for that package. What do you think the environment will be? I could argue this multiple ways. This is down Can be anything? Yeah, okay. Ah, that's the other answer. Okay, right. So like this lambda term has some free variables, and over there on that side, right? That's how I've been motivating closure conversion. I've been saying, okay, you know, we take this lambda and we turn it into a package, and so we have to think of free variables of this and transform it into an environment, etc. Okay, what are the free variables of this lambda?
They came with magic function that gave twice.
They were given in the by the magic function when we were writing the compiler. Now we are not writing the compiler. This is a very good point to sort of say you need to do a mental shift. What you are writing down now is a specification of what it means. It's not even a specification of what it means for the compiler to be correct, so that's what will fall out. But it needs to be a specification that's independent of the compiler. All you know about the compiler is its type translation. You should not be looking at the compiler's term translation when writing down this specification. This is an extensional specification. All you've been told is you need to relate terms of type tau to terms of type tau plus. That's it. Tell me when they should have the same meaning. That's what you're writing down. So you're writing down correctness spec, or relationship spec between source code and target code. Okay? So let's go back to this question of, it seems that since we're doing code computation, we want to put the variables of this. Those are the things that need to go into the. But remember, this value right here, what are its free variables? They're on 10. So what does that tell you? What is our environment going to do? No. Yes, thank you. Vigorous head shaking sideways. Okay, that was leading you down the wrong path. Okay. It would seem that it would need to be empty based on, oh, this is what the compiler is doing, this is what the transformation is doing. But no, the power of this whole technique is that you don't care what this environment is, right? What you want to do is you want to allow anything there, anything at all. So we're just going to say that somehow we don't know what, okay? And for the other two pieces, we know that they have to be a pair of values because we have to stick in a value there between the value relations. So they have to be a pair of values. That means that this value, which is a function relative to lambda, and that means that this value environment will also be a tuple of values. Those are the things that you know, and that's it. Okay? All right. So, okay, so I said that it has to be a value, so it has to be a function. We know that this function has to take two inputs. The first one is an alpha. An alpha needs to be replaced by its witness type, tau n, right? So it needs to take whatever this tau n is, and we don't know what it is, right? It will take that, and then it has to take something of this tau 1 plus, translation of this argument. So, x colon tau 1 plus. So notice this is taking a black x times tau 1, this is not taking a red x tau plus. Okay, do we know anything about the body of this function? We do not. Again, you're doing extension. You are not writing this knowing what the compiler has done. You're writing this based only on what you know from the text. So, and the fact that this is a value, right? That's all the information you're allowed to use. So, just going to put an arbitrary variable here. We don't know what this is. We just know that it's that. Okay, and then we're going to pair that up with the value environment, right? And again, I said that since these are values, whatever we have in that position will need to be some Vn that has this type tau n. And that's all we know. In fact, we don't even know this. Is there anything in this type that tells us that this alpha needs to be equal? No. We better not do that. We better not be talking about this as equal. That would be wrong. So it's just a tau n, and here we have a Vn such that Vn has type tau n. Okay, so I claim that that is the canonical form of values that you can put over here that have the right translation type, which is this. Okay? We're not allowed to sort of refine this any further. Okay, so these two things. Now, what have we been doing for whenever we write the value relation for functions? We say two functions, yesterday we said two functions of type tau and type 2 are related. If you give them related inputs, and then they give you related outputs, right? So two related inputs, two values that are related, and the argument type is tau 1, and I will give you, after substitution into the body of the lambdas, I will give you something that is related to add as expressions as type tau 2, right? Okay, let's do that exercise. It's just that we have to do this happy exercise. So what do we do? Right, for all inputs that you can give to these functions, right? So for all black B and red B, such that they are related in B of tau 1, which means that this guy will have type tau 1 plus, So give me 2 inputs for my functions on the 2 sides. Now we want to do the application. Say whatever we get after that is related in the relation and the result in calculation, right? For all of those, we want to say that, okay, this requires just a little bit of spelling out. You have a path here, but you're trying to do an application now, right? Just like we saw when we were doing this for the unpack, we're basically going to have to take this path, we're going to have to unpack it, then we're going to have to take the first thing out of this pair out, apply it to the second thing from the pair, right? And then apply it to the input, which now is this red thing. You with me? Okay. So I'm not going to write it as an unpack of this entire pack. Let's just sort of pretend that the unpack of the pack takes a step exactly like this. So I'm going to write out what we get on this side. Okay? What is that going to get out? We get the body of this function, right? Oh, let me do the first side because I haven't done that. Okay, so we're going to take the E, the black E, we're going to put in the source argument, replace the S. Good? And we're trying to say that this is related to something on this side where we have the red E. And what do we substitute for as inputs?
Vn
Vn for
Z
and
and
this red
the
E.
value will be for it.
Great. Just doesn't done a big thing. We're written down a specification of when source code and target code is related, at least for the value. So we can quickly finish this up with expressions because that is much easier. So, and E, how we want a black expression E and a red expression E to be related when what? We're going to do what we did yesterday. We're going to run them down to values and tip the values. If they terminate, the values have to be related. Okay? So we're basically going to say, for all BS such, for all black B such that this guy, now this is a terminating language because I didn't throw in recursive, so I'm not doing that the next minute. I'll be a little faster. So if E evaluates to black B, then it must be the case that there exists a red B such that red B evaluates to the red B, and then those two things have to be related.
Could we have used application in the previous case instead of kind of re-implementing the substitution?
Right here?
Yeah, so could we have kind of constructed an application instead of that application evaluate constructed?
So by application, you would basically be saying that you're defining some other shorthand called what's called app, which takes one of these paths, unpacks it, and then something like that.
So I guess you're using what that arrow there?
Oh, I see over here. This is an implication.
Oh, sorry.
For all B such that
Okay, but you have, okay, so you're using the step, right? You're using step star.
yes, that's
So
that's
could
it's
we-
reduced down to a value.
Yes, so we have constructed an application term there of the lambda to the argument expression, and then use the step.
Yes, you can.
And then that instead of kind of re-implementing the step and.
I see. Yes, you're saying that I'm writing the term that came after the step. Can't we just like right in here sort of say that if the unpack of this in a certain way, do the application properly, steps to something, then we just need to be related to that something. Yes, that's fine. I just think that will end up more clear. Depends on how you define it. But it's fine. It's the same, conception is exactly the same. Because we are writing down precisely what we get after taking that. You're right. Similarly on that side too, right? I've been doing this for the last 2 days. Here, you could have said A source term and a target term are related. If the source thing evaluates to a v, that the target, so imagine that we did, so I want you to sort of step out of this exact scenario and imagine that you do have a non-terminating definition, then think about the point of view, right? So this is then saying that if E evaluates to V, that actually terminates, and we can step in this here, then this side must also terminate and the values will be related. Do we want and the opposite direction for all red V such that this thing terminates, then it must be the case that there exists a black V such that this terminates and these two V's are related. Remember we did this symmetric thing yesterday? We talked about it. So I'm sort of asking, should it be a symmetric definition here or an asymmetric one? We could talk about this offline quite a lot. I'm going to leave that. I think you want the symmetric one. Because it's about, like, especially I think once you start thinking about non-termination, what does it mean for these two things to be equivalent? So you know that if your target terminates, your source does. But you don't, sorry, the other way. You know that if your source terminates, then your target does. But if you don't know that when your target terminates, your source does, what does that mean for compatibility? Yes?
So you could compile independent proofs to basically whatever you want.
Yeah. And do you want to?
You can observe that.
Yeah. So that would be, that's when you want this to be symmetric. You really want it to be there. And now we do the completely standard thing of defining a G relation. So, empty context, empty substitution, non-empty context, X colon tau. We have gammas that now map X's to black B's with red B's, right? And we want to say that gamma belongs to G big gamma, and the black B and the red B belong to B of that type tau. I mean, partly what I want you to get out of this is that certain marks and logical relations are just so easy to lift up to this final, right? Just keep the invariant in mind, which I put up for you at the very beginning, that these are the shape things that we are trying to relate. Just be faithful to that and keep carrying it out and just scaling your logical relations, binary plus language, right? And then finally, at the very top level, we can define this ES, logically related, if you will, to NTT. Said I wouldn't write NTT, but no. Then how do we define that? And this has to be indexed by the type on this side, right? So here I'm assuming that ES has type tau under gamma. Let's actually write it out. ES has type tau under gamma, and under gamma plus and dot, ET has type tau plus. Okay, well type terms, we relate them. And for all substitutions, little gamma in G of the source gamma, you want to be able to use gamma. So notice now your gammas are mapping to source things and target things. Remember yesterday I said I'm going to say, whenever a gamma maps to two things, I'm going to write gamma subscript 1 to extract out all the X maps to B1s and use that as a substitution. And do gamma 2 and it's in order to say X maps to the second thing and use that as a substitution. I'm going to do exactly the same thing now, only I'm going to write gamma S, so extract the X maps to source things substitution, apply it to the source term. That needs to be related to gamma of T, the other side, T, which you are applying to ET, right? And these two things need to be related as expressions at the time. Fundamental property. In this case, it is giving us compiler correctness. on the structure of this typing derivation, right? The structure of this typing derivation is driving the structure of the type translation, of the compiler translation. And so you have one case for every single type you go through the source, and you will prove that the original thing is related to the compiler thing. Right? They're in the logical relation. All right. Any questions? Okay, yeah.
Basically, gamma, S and gamma, B.
Okay, so gamma, if your black gamma is something of the form x1 maps to b1, b1, etc., right? Then I'm writing gamma s to mean extract. S. I'm writing gamma s to mean get the mapping from ZX. No, sorry. Black. Yes.